I'm David Fouhey, and we're going to be hearing from about trustworthy and robust machine learning. We're going to be hearing from two new members of the lab, Maggie Makar and Michal Derezinski, who joined just a few short months ago. And so these are going to be two exciting talks. And so first we'll hear from Maggie Makar, who's a presidential postdoctoral fellow. Her research interests lie at the intersection of machine learning and causal inference. Her work leverages causal ideas to make ML models more robust to distributional shifts. And she uses ideas from machine learning to make causal inference more statistically efficient. Her work has appeared at ICML, AAAI, JAMA, Health Affairs and Epidemiology, and she joined CSE after a PhD at MIT and EECS. So she'll be presenting on causally motivated shortcut removal using auxiliary labels. So please take it away, Maggie.
Awesome. Can people hear me? Yes? Okay, cool. All right, let me start sharing my screen here. All right, cool. Thank you for the introduction, David. I am going to talk to you today about how we can build reliable prediction models using ideas from causality. Specifically, we'll look at robustness to what we call shortcut learning. And the narrative in the last few years has been that we can build super accurate models, and specifically deep neural networks, that are great, excuse me, at predictions. So here in this image, we're able to predict that a healthy male does not have pneumonia. But what we've seen is that they're increasingly reliant on shortcuts, which for now we'll say that these are spurious correlations that exist in the data. And when these spurious correlations break, the model no longer gives the stellar accuracy that we see at training time. So in this image, the model mistakenly predicts that a healthy woman, or in general, healthy women have pneumonia. In this case, we say that the model is using sex as a shortcut to predict pneumonia. And more generally, shortcut learning happens when the model relies on these spurious correlations that exist at training time, but break at testing time. So the question we're asking in this work is, can we build models that are robust to these shortcuts? And we're going to assume that we have access to an auxiliary label at training time, but not necessarily at test time. And in this example that I'm giving, the auxiliary label is the sex of the patient. And the key idea here is that we're going to approach this problem and look at it from the lens of causality. And we're going to pull ideas from causality to improve this prediction problem. And this approach will take us to a solution that kind of looks similar to things that we've already seen in existing literature, where we end up minimizing something like the prediction loss while imposing an invariance penalty. While this approach looks similar to other things that we've seen, there are key distinctions that are motivated by our causal view of the problem. So let's dig into that pneumonia example just a little bit more. Here we have X-ray images, and we want a predictor to tell us if the patient has pneumonia or not. And at training time, we have the X-rays and their labels. So the label Y is 1 if the patient has pneumonia. And we also assume that we have the sex variable, and we'll use V to denote that variable. Now, let's say that at training time, we don't observe many healthy females. Maybe women in this county are like too busy to get an X-ray, and they only show up to the hospital if things are really, really bad. And let's say that for some reason, men's pneumonia cases are routinely rerouted to the hospital next door. So, or rather, yeah, so we only see unhealthy, or we don't see many unhealthy males. What happens at test time, if we're not careful, we might end up with incorrectly predicting that a healthy female has pneumonia, just because our model has learned to encode, say, representations of something like the breast tissue as a shortcut. So how does viewing this problem from a causal perspective help? Before we ask even that question, we should ask, what does it mean to look at this problem from a causal perspective? We'll start by defining the causal directed acyclic graph, or causal DAG. The DAG is just a graph where solid arrows encode causal relationships between variables. Shaded nodes in the graph mean the variable is observed. White nodes are unobserved. And we've already introduced Y and V. X here is the pixels of the X-ray. And we see that the main label affects X through this variable X star, which is unobserved. And you can think of this X star as the visual cues that are characteristic of pneumonia in our example. The other thing that you'll see here is this bidirectional arrow, which is dashed. And this arrow shows that the two variables are correlated but not causally related. So what we want is a predictor that is invariant to any correlation between V and Y. To define things a bit more formally, we have some source distribution PS, and we want a predictor F, which is the composition of the learned representation phi and the final classifier H. And we want this F to be accurate, and we want it to have the same performance across members of this family of target distributions. Members of this family are the same as the source distribution, except that they can have different correlations between V and Y. So this shows us the first advantage of looking at the problem from a causal perspective, which is that it allows us to define a set of naturally occurring distribution shifts that we want to be robust against. This causal perspective also helped us chart a way to a good solution. So we used ideas from causality to analyze how different models perform when trained using finite samples or limited samples, so non-asymptotic regimes. And what we found is that there exists an ideal distribution, and here I'm denoting it with P circle, and that is a distribution where there exists no correlation between V and Y. In other words, in this distribution, we're equally likely to observe healthy females as we are likely to observe females with pneumonia. Now, let's pretend for a second that we've sampled from this ideal distribution. What we found is that in this setting, by imposing an invariance penalty, which encourages the model to encode independencies that are implied by the causal DAG, this kind of invariance penalty leads to more efficient estimators without introducing bias. And we'll look in a second at how exactly we enforce this penalty. But first, what does this proposition mean? Think of a simple example where we have two features. The first one affects the value of the auxiliary label V, and the other affects the value of the main label Y. And again, to keep things simple, suppose we're considering only linear representations, phi, and the final classifier is just the sigmoid transformation. So this is an overglorified logistic regression, basically. We know that the optimal weights WV should be equal to 0. So the real function space that we want to consider is this line, which allows WY to take on non-zero values, but it sets WV to be 0. Now, if we decided to do L2 regularization, our candidate function space becomes this yellow circle. Instead, enforcing a kind of causally motivated regularization penalizes the learned representations that encode information about V, and in doing so, it reduces the complexity of the function class. So by imposing this independence penalty, we can reduce the function space to something that, roughly speaking, looks like this blue oval. And this penalty allows us to reduce the hypothesis space without introducing bias, which then translates into a smaller generalization or finite sample error. So that means that causally motivated regularization schemes give us not only robustness, but also finite sample efficiency. Unfortunately, none of this holds when we sample from any distribution other than the ideal distribution. So we turned again to ideas from causality to address this issue. In causality, we often have a notion of an ideal distribution, which is the distribution of a randomized control trial. So we often reweight the data in order to mimic independencies that exist in a randomized control trial. And we did something similar here, where we used weighting to map us onto a distribution that looks like the ideal distribution. And this helps us recover nice independencies that exist in the ideal data. How does this translate into an optimization objective? Our objective will be to minimize the weighted logistic loss and a penalty term. Alpha is a hyperparameter that we pick during cross-validation, and the penalty term here is the maximum mean discrepancy, or MMD. I won't go into the details here, but if the MMD is 0, that means that there's no information encoded about V in the representation, and that's a good thing. Importantly, both the loss and the MMD are weighted by this inverse weights that I defined in the slide prior to this. So how does this all work in practice? We wanted a data set where we can control the correlation between V and Y at training and at test time. So instead of using natural images to empirically validate our approach, we simulated data where we took images of land or water birds and superimposed them on land and water backgrounds, as you see on the slide. This is similar to setup by Sagawa et al. The task here is to predict whether the bird in the picture is a land or water bird. So the main label Y is the type of bird. The auxiliary label is the type of background. And again, it's either land or water. We're going to fix the training or source distribution and look at the performance across many test distributions. So on the x-axis here is the correlation between the background label and the main label at test time. And this dashed line shows where the training distribution is. And on the y-axis, we will look at the AURC at test time. We will compare our model to a bunch of different models. This one just does weight decay or L2 regularization. This is a weighted version of L2 regularized models, which uses the same weights we use, but it does not have the MMB penalty. And then the final model, this random augmentation model, it uses transformations such as random crops, rotations, and brightness to augment the data at training time. And we see that our approach gives a better AURC at every target or test distribution. Really quick, I'll show you some results on a less contrived data set. Here we use the data set of chest x-rays, and we downsampled females who have pneumonia at training time. And this is similar to a setup that was introduced by Jabor et al. The task here is to predict the onset of pneumonia, which is our main label, while making sure that sex is not a shortcut. And again, we see that our approach has a better AURC when there is a distribution shift, which is the top row. And within distribution, it does almost as well as the best model. To sum up, I've showed you that causally motivated regularization schemes lead to robust and efficient models. If you're interested to dig into this more, it's up on archive, and I will be taking questions in the next session.
Thank you, Maggie. Yeah, so there are a few questions that have been chat.
Oh, okay.
One thing I'm going to encourage people. So I think we're to keep on time. We'll have to get to the next speaker, but there's the birds of a feather session, which will give you lots of opportunity to ask questions, which is great. So we'll next hear from Michal Derezinski. His research is focused on developing scalable randomized algorithms with robust statistical guarantees for machine learning, data science, and optimization. So he received the Best Dissertation Award at UC Santa Cruz for his work on sampling methods in statistical learning, and his work on reducing the cost of interpretability and dimensionality reduction won the Best Paper Award at NeurIPS 2020, which is very exciting. He joins us from University of California, Berkeley, where he was a postdoctoral fellow in statistics, and he was previously a research fellow at the Simons Institute for Theory of Computing. And he's going to be talking about what is the cost of interpretability and dimensionality reduction. And so please take it away. We can't hear you.
Okay, I'm muted. Can you hear me now? Great. Okay, thank you very much for this introduction. And so I will be talking about this cost of interpretability, and this is joint work with Rajiv and Michal. Okay, so a core motivation for this work is the notion of interpretable dimensionality reduction. As an example, consider a biological application with a large genetics data set where each individual is described by a sequence of genetic variations called single nucleotide polymorphisms, or SNPs for short. So prior work has shown that such data can be effectively characterized by a subset of SNPs chosen so that it is correlated with the top principal components of the data. This subset can then be used by domain experts to extract insight from the data. And other applications of interpretable dimensionality reduction that have been demonstrated arise, for example, in the context of image and text processing tasks. So the two basic dimensionality reduction tasks that I will consider in this talk are known as column subset selection and the Nyström method. Those two tasks are actually very closely related, even though they often appear independently in the literature. And so the first one on the left is most commonly described as feature selection from a data matrix, where the features are represented by columns. For the Nyström method on the right, the matrix in question is a square kernel matrix, which represents the pairwise interactions between the data points. and we wish to represent it by a small subset of its entries. This task arises, for example, in the context of kernel machines, Gaussian process regression, independent component analysis, among others. There's a close connection between these two tasks, which is why all of the results I will present apply in both settings. So at the foundation of many dimensionality reduction approaches is the fundamental task of low-rank approximation. So here, our goal is to project the data onto a low-dimensional subspace while minimizing a certain mathematically formulated projection error. Without additional constraints, there's actually a uniquely optimal choice to minimize this error by projecting onto the top k principal components in the data. However, typically these principal component vectors will not really correspond to any interpretable features or instances, which is why we may want to choose a subspace that is spanned by a subset of some subset of the data matrix. So naturally, there are other notions of interpretability than this sort of selecting subsets of the data matrix. But this model provides a useful framework for analyzing what can be described as the cost of interpretability. So here we will measure this cost by the so-called approximation factor, which compares the error of the best interpretable representation relative to the optimal non-interpretable choice, which is given by the principal components, and that for a given dimensionality and subset parameter k. So actually, a large body of literature has been dedicated to obtaining guarantees for this approximation factor that describes the cost of interpretability. And so in particular, it was shown that the cost of interpretability in rank k approximation can always be bounded by a factor of k plus 1. And these results are still used as a technical tool in recent works, including the best paper at the 2019 ICML conference, which applied them to sparse variational Gaussian process regression. The above bound is, in fact, worst case optimal in that there are problem instances for which this factor k plus 1 cannot be improved. But these results are still somewhat unsatisfying because they suggest that the cost of interpretability gets progressively higher as the rank parameter k grows, as you can see in the plot. But this is actually not generally observed in practice. So to understand this, we empirically tested the approximation factor for the worst case example given in the prior work. And as we can see, the factor does reach the worst case bound for one value of k, but then it rapidly drops down in either direction. So even for the worst case example, a high cost of interpretability is only a corner case. So to explain this, we went beyond this worst case analysis so that we could accurately capture the nonlinear behavior of this approximation factor. So in particular, these new guarantees show that the worst case example is part of a larger phenomenon, which we refer to as the multiple descent curve in subset selection. I illustrated this here, this curve in the plot here, and both empirically and theoretically. And as we can see, the approximation factor exhibits occasional sharp spikes, but it is otherwise very small. Actually, our new lower bound shows that more than one spike can occur for one data matrix. And we also showed that the spikes are correlated with certain very natural characteristics of the data matrix, as I will explain shortly. Okay, so what properties of the data affect this nonlinear behavior of the cost of interpretability? So for example, do we expect this cost to be smaller if the data is more or less uniformly distributed in the domain space, as in dataset 1 here shown, or if it has some low dimensional structures in dataset 2? Well, first, we need to be able to easily characterize such properties of the data. So for this, we can use the so-called spectral decay profile, which looks at the magnitude of the largest directions of variance in the data, represented mathematically as the singular values of the data matrix. So to illustrate the structure of the data set through the spectral decay, we can plot the singular values in decreasing order. So for example, for the first data set, we see a relatively flat decay with multiple singular values of comparable magnitude, because there are many directions with large variance, whereas for the second data set, there's one or two large singular values followed by a rapid decay. So this corresponds to the low dimensional structure we can see in the top right. So there are several types of spectral decay which are commonly observed in real-world data sets, such as a flat decay, a sharp drop, and a range of smooth decays with polynomial or exponential rates. In fact, often we may be able to anticipate the type of spectral decay even before we look at the data. For example, because of some prior knowledge coming from the domain about the underlying data distribution. And in some cases, we can actually control spectral decay through model selection, for example, by choosing an appropriate similarity kernel. So in this work, we used the spectral decay profile of the data to provide a complete characterization of the cost of interpretability, showing that if the data exhibits sufficiently smooth spectral decay, then the spikes in the multiple descent curve can be avoided. In particular, this allows us to deduce that the spikes in the cost of interpretability are directly correlated with sharp drops in the spectrum of the data. This also implies that when the spectral decay is sufficiently smooth, for example, when it exhibits a polynomial rate, which is commonly observed in practice, then we can prove that there's no spikes and the cost of interpretability is small for all values of the dimensionality parameter, significantly improving on the guarantees from the prior work. Of course, the practical performance of dimensional reduction depends on the subset selection method, on the algorithm used. So here we focus primarily on the method called determinantal point processes. So a determinantal point process is a non-IID randomized sampling method that uses negative correlations to induce diversity in the sampled subset. DPPs have found many applications in machine learning for the past 15 years or so, including in recommendation systems, experimental design, and stochastic optimization. And they can be implemented very efficiently with runtimes faster than singular value decomposition of the data. So if you want to learn more or try this out yourself, I provided a couple of references here, including state-of-the-art implementation and a short survey about DPPs and their applications. So in our empirical results, we showed that the multiple descent phenomenon, which I mentioned earlier, can be observed not only in worst case examples, but also in real world subset selection tasks. Here we demonstrate this for the Nyström method with the Gaussian radial basis function kernel, studying the effect of varying the RBF parameter. On the top plots, I showed the Nyström approximation factor, which corresponds to the cost of interpretability for two benchmark data sets. And at the bottom plots, we compared to the decreasing singular values of the data. And so we can clearly see that the spikes in the approximation factor align with big drops in the spectral decay, and that this behavior is greatly influenced by the value of the RBF parameter. So decreasing this parameter results in a smoother spectral decay, which in turn eliminates the spikes, resulting in a uniformly small approximation factor. The right choice of the RBF parameter ultimately depends on the downstream machine learning task. So depending on the structure of the problem, we may end up in the regime where the approximation factor exhibits a multiple descent curve, or in the regime where it is relatively flat. Here I showed the results we're using a determinantal point process as the subset selection algorithm. However, remarkably, we can observe the same phenomenon even if we switch to a completely different method. This one is called greedy subset selection. So this suggests to me that the multiple descent curve is not something that's specific to DPPs, but rather a sort of a method agnostic phenomenon. So to conclude, in this talk, we studied the cost of interpretability in dimensionality reduction. So in particular, I focused on two methods of dimensionality reduction, column subset selection and the Nyström method, both of which use data subsets to construct small but interpretable representation of large data sets. And in the results, we overcame some limitations of the prior work to accurately capture and explain the nonlinear behavior of the cost of interpretability. And this analysis showed that this is sort of a more this multiple descent curve is as a general phenomenon. And in fact, this can be observed not only in artificially constructed examples, but in fact in real world problems. That's it from me. Thank you very much for your attention.